Hi everyone, and welcome to another AP Calculus video. Today we're going to talk about how the first derivative is going to help us understand when a function is increasing and decreasing. And we're also going to talk a little bit about how we need to test our answers and the evidence we need to give when we describe what's happening on a graph. So first things first, we've discussed this a little bit with the idea of the first derivative being positive or negative and indicating if my function is increasing or decreasing. So remember that a derivative describes the slope of a curve. So if the slopes are positive, like they are kind of on this first, so we have a positive slope, that means you have a positive first derivative. And so notice that my function is increasing whenever I have a positive slope. So over here, I have a positive first derivative, a positive slope. So when the slopes are positive, then my function is increasing. So part one here of this increasing, decreasing intervals note says that if f prime is greater than 0 at each point on this interval, then f is increasing on the closed interval. So notice when we describe an increasing interval, we include those endpoints, and that just has to do with the definition of being increasing. You need to include the point in the interval of increasing and decreasing, so we use those closed brackets. And it has to do with the definition. You need a second point to compare to. So you need to include the endpoint so you can compare any point before the endpoint to that endpoint, if that makes sense. So it's increasing up to and including that endpoint. The same is true when we talk about decreasing. The slopes will be negative. So here, anywhere we have our function decreasing, we have a negative slope or a negative first derivative. Remember, the slope and the first derivative are the same thing when we're talking about our curves. So anywhere we have a negative first derivative, that means the slopes are negative. It means our function is decreasing. And then, of course, where do we find where those breaks are? Well, they happen when f prime equals 0. So f prime equals 0 at max and min points, at those extreme values. So if we can show that the derivative is 0, then we know that we're probably increasing or decreasing on one side or the other. Occasionally, though, keep in mind, just because you know that a derivative is 0, hey, look, we're positive over here and we stay positive. So it is possible to have a scenario where my function is continually increasing, even if my first derivative hits a value of 0. It just means that we didn't hit a max or a min. We just leveled out and then kept on going. So let's take a look at some problems here and find some local extrema and identify where my function is increasing and where my function is decreasing. So the first thing I'm going to do anytime I'm looking for extrema is I need to find my critical points. Remember, critical points are values where my derivative is 0 or undefined, or if I have endpoints, it could also include the endpoints. Here, I don't have endpoints, I don't have an interval, and I have a nice well-behaved polynomial function, so I'm not going to have any undefined values. The domain for this is all real numbers. So all I have to do here is figure out where is f prime of x equal to 0. So I need to find y prime. Okay, so y prime is 3x squared minus 4. And I'm going to set this equal to 0 and solve. So 3x squared equals 4. X squared equals 4 over 3. So x would be plus or minus the square root of 4/3. Now, I'm not going to simplify this because this is big kid math. We don't need to simplify this and waste our time. Plus, you're going to find out that just leaving it alone here is actually going to make it easier in the long run when we try to identify what's happening. Because now that we've figured out our critical points, what's happening, and I know this because I know what a polynomial looks like. I know that when I have a third degree polynomial, it's going to go kind of like this. And I know the end behavior because I remember these things from previous math classes. But you don't have to remember that. It just kind of gives you a leg up. But what's happening here is that these are the 2 points that are possibly, not guaranteed, but possibly max or minimum points. So what I'm going to do is I'm going to create what's called a sign chart. And we've seen these before. I'm going to label it f prime because very soon we're also going to be discussing second derivatives and what they tell us. So we'll be making sign charts for the second derivative. Now here's the deal. The reason why I leave these here is because when I put them on my sign chart, I need to pick values in between and to the right and to the left to figure out what's happening. And the idea here is I need to know what's happening in my derivative. So I want to figure out, is my derivative positive or negative in these 3 spots? So the first spot I'm going to pick is in between because I'm going to remember that x equals 0 is between these. So I'm going to pick 0 And basically I'm going to find f prime of 0. And I don't even need to evaluate it. I just need to see, is f prime of 0 positive or negative? Well, remember, f prime is this 3x squared minus 4. When I put 0 in for x, I get a negative 4. So I get a negative there. So if you need to write it out, go ahead. And, you know, I wouldn't even write things down. I would be punching it into my calculator if I have that handy. If I can't use a calculator, I'd be kind of like doing some mental math. But remember, we're not going to put these values on our number line. Notice that mine are down below. I don't ever put it on my sign chart. The only thing I put on my sign chart are my critical values. So these two values that I found right here where the derivative is 0. And then the only other thing that I'm going to put up here is that it's negative in the middle. Okay, so that means it's decreasing between those 2 points. So now I'm going to go beyond. And here's the tricky part. And here's why I said leave it as 4 over 4/3, the square root of 4/3. It's because I need to pick a nice easy value. And so I need the square root of something over here to the right. So I don't know. How about the square root of 6/3? Because that's the square root of 2, right? And I know that 6/3 is bigger because 6 is bigger than 4. So it follows that now it's easy to pick. And the reason why I like square root of 2 is because when I do f prime of square root of 2, I'm going to be squaring that number, and I'll have 3 times the square root of 2 squared minus 4. Well, that's 3 times 2 minus 4. That's positive 2. So over here, I have a positive value for my first derivative. And if I go over here to the other side, I'm going to pick a similar value. I'm going to pick negative square root of 6/3. And when I put that in, negative square root of 2 squared, it's actually going to give me the exact same value. So I know that I'm going to be positive on this side as well. So what does this tell me about my function? It tells me that I'm increasing. So I will often take my sign chart and I'll go like this. I'm increasing, increasing, increasing until I get to that critical value, where then I begin to decrease, and then I get to the next critical value, and then I increase. So this green is my function. It's not the derivative, it's the function. And so now I can take from my sign chart and I can identify, oh, look, I have a max right here and a min over here, and I can see where I'm increasing and decreasing because I've made this sketch on my first derivative chart. So let's go ahead and sum it up. So I know I have a max at x equals negative 4/3. I know I have a min at x equals positive square root of 4/3. And I know that because I have a sign change, because f prime equals 0. I always want to make sure I understand my justification. And f prime changes positive to negative. And then over here, f prime changes negative to positive. So I need to give those 2 pieces of evidence there. So for my max and my min. And then here's where I'm going to say I'm increasing. All right, so I'm increasing up to negative square root of 4/3. So let's see if we can reframe this and see it a little bit better. So the way I'll write it is this: from negative infinity up to negative 4/3. And remember, increasing, we use those closed brackets on the numerical values. Infinities are always open. And then I'm also increasing. So let's make sure we see it. So here's where I'm increasing, and then over here I have a second place where I'm increasing. So I'm going to say close bracket, square root of 4/3 to positive infinity, and then I'll be decreasing in the middle. It's weird because it feels like we're saying we're both increasing and decreasing, but all we're doing is we're saying this is the interval. So you need to include the endpoints in both the increasing and the decreasing intervals, because you need that point to be able to compare to, because that's the definition of being increasing or decreasing. So here's one example. Let's make sure we answered everything. Local extrema, maxes, mins, interval of increasing and decreasing. Check. Let's try another example. This one says find the local extrema and intervals where f is increasing and the intervals where f is decreasing. So here we go. We are going to need to do the product rule on this particular problem. So this is, here's u and here's v. I'm going to rewrite it like this, x and then 3 minus x squared to the 1/2 power. So here we go. I need u prime. U prime is just 1. I need v prime. Ooh, I'm going to have to use the chain rule here also. So v prime is, so this is v. So 1/2 times 3 minus x squared to the negative 1/2. Ooh, this is not going to be fun. And then I need the derivative of that inside. So the derivative of the inside is negative 2x. Ooh, tricky. So let's clean this up a little bit. V prime, let's see, the negative 2 and the 1/2 cancel. I'm going to still be left with negative x. And then I'm going to go ahead and drop that guy down. 3 minus x squared. Yikes. Okay, so now let's use our product rule. Here we go. So f prime of x is, okay, so remember it's uv prime plus vu prime. So here we go. U is x. V prime, here it comes, negative x, 3 minus x squared, plus v times u prime. U prime is 1, so that's easy. Oh boy, let's clean this up. We get negative x squared over the square root of 3 minus x squared plus the square root of 3 minus x squared. Now remember, our goal here is to figure out where our critical values are. And critical values occur at endpoints, which we don't have here because we have, it's all real numbers. We don't have that happening. Or there's no specified endpoints anyway. They also happen where the derivative is 0 or where the derivative is undefined. And I have a fraction going on here. So this first term is a fraction. So remember from the previous video we talked about finding those extrema. We find extrema where f prime is 0. That's where the numerator of a rational function or a fraction function, where the numerator is 0. And then we're undefined where the denominator is 0. So we have to take this function and we have to make it one fraction. And the way that we're going to do that is by finding a common denominator. So I'm going to take this second term and I'm going to multiply it by the square root of 3 minus x squared over the square root of 3 minus x squared. And what that's going to do is in the numerator, the square roots will cancel each other out and we'll end up with this. We'll have negative x squared plus 3 minus x squared. And then all over that common denominator. So now when I kind of clean this up some more, I'll get negative 2x squared plus 3. Whew. This one's a doozy. Okay, lots of algebra. So this is my derivative. Now I haven't even found my critical values yet. So I have to take this and set it equal to 0, and then I have to take the denominator and set it equal to 0. So that's where it's going to give me my 0 values and my undefined values. Because remember, critical points happen where the derivative is 0, where the derivative is undefined, or at endpoints, which we don't have here. So without further ado, negative 2x squared plus 3 equals 0, minus 3 minus 3. X squared is going to be 3 halves, right? So x equals plus or minus the square root of 3 halves. I'm just going to leave it, right? So there's 2 critical points. Now I'm going to take the denominator. I'm going to say, well, square root of 3 minus x squared, that's going to be 0. Square both sides, add the x squared over. X is going to be plus or minus the square root of 3. Whew, we got a lot of critical values here. Time for a sign chart. So these are my critical points. So critical. Now, we don't even know what's happening. These are not guaranteed maxes or mins. These are candidates. Sometimes we're going to refer to these as candidates. This is the candidates test, right? Now we have to see if we increase or decrease. So I've got to plot these guys on the number line. So I'm going to have 4 values. So let's see, negative square root of 3, negative square root of 3 over 2, positive square root of 3 over 2, positive square root of 3. That gets them in order. So here we go. Let's start with the easy one. Let's plug in 0. So remember, my derivative here, I'm going to go ahead and rewrite this. F prime was negative 2x squared plus 3 over the square root of 3 minus x squared. So this is what I'm going to be plugging it into. So F prime sign chart. Always label everything. Okay, here goes. Plugging in 0. When I plug in 0, remember, it's not about getting the actual numbers. It's just about seeing, is the result positive or negative? So when I plug in 0, okay, I'm going to get 0 plus 3. So I'm going to have positive in the numerator. And in the denominator, 3 minus 0 is a positive number. So I'm going to have a positive over a positive. So I'm going to be positive in the middle. So now I'm going to go over here in between. Now, oof, this is weird. So here's the deal, you guys. 3 halves, this is the square root of 1.5 and the square root of 3. So what number is in between? How about the square root of 2? So square root of 2, let's do that. Negative 2 times the square root of 2 squared plus 3. Okay, so that's going to be that's negative 4. That's going to be a negative in the numerator. Remember, I don't even care about the number. I just, is it positive or negative? And then let's see, square root of 3 minus the square root of 2 squared. That's 3 minus 2. That's going to be a positive, so I'm okay. So I'm going to be negative in there. Negative over a positive results in a negative. So now let's go over beyond here. Let's use like a value like square root of 4, right? That's 2. So we'll use square root of 4. Negative 2 times square root of 4 squared plus 3. So that's going to be negative 8. That's going to be a negative in the numerator. And then in the denominator, I'm going to have the square root of 3 minus square root of 4 squared. 3 minus 4. Ooh, that's going to give me a negative. That's going to give me the square root of negative 1 in the denominator. I'm imaginary over here. And so what this tells me is that the derivative doesn't exist. Well, doesn't exist. Now, there's a couple explanations for this. If the derivative doesn't exist, that means we must have some sort of weirdness happening. So the derivative doesn't exist at corners, cusps, discontinuities, and vertical tangents. But it also doesn't exist if the function doesn't exist. So if you're getting a value like this, and it's in an entire region, it's probably not a singular point of discontinuity. It's probably not a corner because you're testing a region. So what this tells me is that everything in that region would result in the derivative not existing. So you don't just have a single point where it doesn't exist, you have a whole area. So this is an indication that in the original function, there is no value beyond the square root of 3. And we'll take a look at the graph and I'll show you what I mean. But what's going to happen, the nice thing about these problems is that once I do one side, if everything's being squared, I'm going to get the same results in similar regions on the negative side. Because when I take negative square root of 2 and square it, it becomes a positive. So because I'm squaring everything in the numerator, squaring everything in the denominator, I'm going to get the same answers here, negative and positive. And I'm going to get a negative in the numerator. I'm going to get an undefined value. It's going to be imaginary. So that tells me that there's nothing here and there's nothing there. So what is happening? Well, so far I know this. I know that my function starts somewhere here at negative square root of 3. Because this is negative, it decreases. So it has to be decreasing between these two tick marks. And then it gets to here, and then this positive value says that between these two tick marks, I'm increasing. And then all of a sudden I change and I'm decreasing again. Okay? So I can see where I'm increasing and decreasing, and I can see that I have a max here and I have a min here. And technically, if these are endpoints, I can also classify them as maxes and mins. If I start from the top and go down, it's a max. And then on the other side, wherever I end up, because I'm going down to it, this is a min. So think about your endpoints. If it's the highest spot and you can only go down, then it's a max, right, from your starting point. On the right side, if you're going down to it, it's a min. If you're going up to it, it's a max. So, you know, having the pictures is a nice thing to help you out with this. But let's kind of classify everything that we have going on and kind of wrap everything up. So we want to know where are maxes and mins. We have a max at x equals negative square root of 3, and at positive root 3 over 2, we have a min at x equals negative square root of 3 over 2 and positive square root of 3. And that's because we have f prime is 0 or undefined, and we have a sign change. Now, these are actually going to be endpoints. We'll see that in just a minute. But essentially we have the sign change, we have it undefined and 0, and then I'm going to put a little asterisk because technically these are endpoints. They're just not defined in the problem. So now let's take a look at our increasing and decreasing. We are increasing on the interval negative square root of 3 over 2 to positive square root of 3 over 2. Remember, we use closed intervals. We are decreasing from negative square root of 3 to negative square root of 3 over 2. And from positive square root of 3 over 2 to positive square root of 3. So there are my increasing and decreasing intervals. And if we kind of take a look at the graph of this guy, I'll show you what it means, what's actually happening. So here is a visual of what's happening. So the red function here, this is our original function that we just figured out, and I labeled the critical points here, and you can see that we have these endpoints at square root of 3 and negative square root of 3, and there's no function beyond. And if you think about it, that should make sense, because remember, the domain is all the values I can plug in for x and get a real number back. So anything beyond square root of 3, I'm going to get a negative value under the radical, and it'll be an imaginary number. So our derivative is restricted by any domain restrictions that happen in the original function. So if the original function doesn't contain those values in its domain, then the derivative will not exist beyond those two endpoints. So this is one of those scenarios where if you have a domain restriction, it's good to be aware of that, and that's why we always investigate critical values where the function is undefined, where our derivative is undefined, because it's undefined everywhere beyond the two endpoints. And you can also see that, yes, we're decreasing and then increasing and then decreasing, just like we predicted with our little drawing. So decreasing, increasing, decreasing. So I hope that this has been an enlightening thing for you. The toughest part about this is the algebra. And so the best way that you're going to get good at finding these critical points and being able to determine where am I increasing, where am I decreasing, is simply by practice. And remember, on the AP exam, what you're going to get tripped up with is you're going to forget to make a sign chart, and you're going to forget to look for intervals of increasing and decreasing. Because remember, it is possible to find a critical point that is neither a max nor a min. And so your function might show increasing, increasing. So you might have two intervals next to each other on your sign chart that are both positive, showing that we increase, level out, and keep going. So always make those sign charts. Always test every point, and always remember your endpoints. That's where you're going to get tripped up on your AP exam, is forgetting to make your sign chart and look for that change in increasing and decreasing, and then also checking those endpoints, because those are the tricky parts. So I hope this has been helpful. Keep at it. Keep practicing your algebra. You're not going to get good without practice, and sometimes practicing can be painful because it's a challenge for you and it's frustrating. But my encouragement is just keep at it. No matter how frustrating it seems, you're not going to get through it until you practice, practice, practice. Practice makes proficient, right? And then we just aim for mastery, which maybe sometimes comes, and it happens less than maybe we'd like to admit. So keep at it. You can do this. You've got it.